Alok was pursuing his PhD from Bose Institute, Kolkata, under the guidance of Professor Dipankar Home. After completing his PhD, he went to South Korea to join there as a postdoctoral fellow. Then he went to France for his second postdoc, and after that he went to Japan as a JSPS fellow. He then came back to India to join NIT Patna as an assistant professor. Now, uh, at present, he has moved to IIT Hyderabad and joined there as an associate professor. His research interest is very wide, and he is interested in quantum information theory, quantum communication, quantum foundations, quantum cryptography, and quantum metrology. But today, the topic of his talk is device independent self-testing of unsharp instruments and degeneracy breaking measurements. So with this short introduction, I would like to invite Dr. Alok to present his talk. Dr. Alok.
Yeah, thank you, sir, to that this kind introductions, and that can for a long time. And we are the co-author of quite a number of papers. It was really pleasure to once again. So let me share my screen. Is it okay?
Yes.
Okay. So as you said, that I shall be talking here in this lecture, that is self-testing of quantum instruments and degeneracy-breaking. In this talk, I shall be little. I mean, there are mostly students, and except
Alok, interrupting.
Yeah.
Your slide is not visible now.
But it is visible to us.
Okay.
Is it visible?
Yeah, yes.
Okay, fine. Continue.
Now, can you see it or not?
No, in my screen it is not coming.
To our screen it is coming. Have you
okay,
mistakenly?
Let me reshare also. Now?
To us it is visible.
I don't know here it is shown that the account owner and everyone in the meeting can save this live transcription has been enabled like this. It is showing.
So what me?
You haven't pinned him, right? If yes, then you can unpin and see the slides.
Okay, fine. Yes, hello, continue.
Okay. So this is a kind of, it's not exactly the overview, it's a technical talk, but you can ask questions at any time, because I think that except Satura and me and all of us are the students here. So you can ask at any point of time, you have confusion, you can ask questions. It is not the case that I have to finish my talk, but it is better you ask questions and I can try to give answers. Okay. So this work is based on two works published in this year. And the team is this Prabhupada Rai, Sumit Mukherjee, and Samsung Mahathir. There are two students who are there at NIT Patna. So the NIT Patna group is scattered now. All of them submitted their thesis, and Prabhupada is now currently at ISR kind of postdoc. Sumit is a postdoc at ISR Kolkata, and Samsung Mahathir is still at NIT Patna. Okay, let me start. What is self-testing? Self-testing is actually a technical term, which is actually the device-independent certifications of quantum instruments or quantum correlations to the Bell test. Maybe an everyday example would be interesting. That every one of us uses cell phone, because our days and nights are incomplete without the cell phone. But do you know that is your cell phone? You can buy the cell phone from any other companies. I mean, from Chinese, the Korean, Indian, maybe the Indian phones people don't buy much, and the American companies. So, do you have any idea that your cell phone is working perfectly? That means whether any app or any chip is there that is collecting all of your data or day-to-day activity, remote server in some other countries or in the remote location. Actually, it is impossible to know. some point you can check something that is say my whether there's an adversary which is who is watching my phone without my knowledge or not. You can check it, but it is impossible to certify that my phone is working and without the eavesdropper. So how do we do that? What we can do is that we can do only the trust, because you cannot open the mobile phone, and if you open it, you have no idea how it works. And there is no way to know how the inner working works. So you have to trust them. Trust is a very difficult nowadays. I mean, our government also says that you cannot trust some C-type company that is in a problem. So classically, what I want to mean by that is that classically there is very difficult to trust someone, because there is always the companies is there. You have no idea about the inner working of the mobiles and whether your data is being stored by a remote server. Can you do better in quantum theory? The answer is yes. So which is the self-testing? That means without knowing the inner working of the devices, only by knowing the input-output statistics. In the mobile phone, you give some input, you get some output. So from this input-output statistics, whether you can certify that my device is working perfectly and there is no adversary who is watching my mobile phone and without my knowledge. Classically, in our everyday world, this is impossible to certify. You have to believe in the trust, but in quantum theory, we actually can characterize, we can actually certify the untrusted devices, the black boxes. Why it is important? It is important for many reasons, because today is the era of security, and we want the unconditional security. And self-testing is the OS, self-testing is the protocol that gives the unconditional security, and it works with the quantum principle. For example, there's a quantum device-independent quantum cryptography, device-independent randomness certification, and certification of extremal correlation. These are all the significance of self-testing. So self-testing is very important. And Bell's theorem is actually provides. Bell's theorem actually have a unique power that actually provides us the self-testing. That means uniquely characterize the correlations. So what is the device-independent scenario? There are two black boxes. The left one belongs to Alice and right one belongs to Bob. And they are receiving, as I mentioned, only the input-output. The Alice is receiving the input X and Bob is receiving the input Y. And they're producing the output A. What you know is that the observed statistics, that you can press a button that selects 0, you can press a button that selects 1 here, and then you can get the output. And then what you can calculate is the input-output statistics, P, A, B, X, Y. So there's a set of probabilities, set of joint statistics you can collect from these devices. The task is that whether I get the joint statistics I obtain that are unique, and that can self-test, that can certify that whatever the devices I'm using. So I refer to a recent review by Supik and Bowles for this more about the device-independent self-testing scenarios. So once again, what is device-independent self-testing? So here in the whole talk, I shall be mentioning that the self-testing means it's a device-independent certification. The self-testing is a device-independent protocol that aims to uniquely characterize the nature of the black boxes from the observed statistics. So what you have in hand is only the observed statistics. From there, you have to decide, you have to know the nature of the black boxes. So in quantum theory, this is any operational theory, but in quantum theory, there's a source that is S, the source that produces the states that can be shared by both Alice and Bob. And in quantum theory, the state is nothing but a density matrix. So we can calculate the observed statistics, P, A, B, X, Y rho by the help of boundary. What is this? That is trace rho AB, and this is measurement operator AAX of the Alice and BBY to the Bob. So this we can calculate from quantum theory, and our task is to prove that this type of joint statistics are unique, and they actually uniquely characterize the nature of the black. So I'm quickly going through the simplest scenario of device independence testing, which is the Bell-CHSH scenario. The CHSH is the Closer-Hahn-Simonian fault. You may know that this Closer actually the C of this CHSH, the Closer. He recently got last year he got the Nobel Prize for this contribution to the Bell test. The Bell test consists this one, the simplest one. That is, there's two parties, Alice and Bob. Alice receiving input X, Bob receiving input Y, and they produce the dichotomic outputs, that is plus minus 1. So the most important quantity here is that, let's say, joint probability. It is P, A, B, X, Y. So this is called the P is called the behavior. This is a set of probabilities. So S is the source here that emits the physical systems. It can be classical, it can be quantum. In a classical theory, commonly we say it's a hidden variable theory where S produces, say, a randomness, that's a lambda, the ontic state or hidden variable. In a classical theory, what we can assume that this lambda actually, the classical theory means it's a local realist theory where realism and locality are two assumptions that are imposed on this lambda level theory. The realism actually means is that what this lambda ontic state can predetermine the value of the Alice's involved measurement. And locality says that outcome of Alice is A is independent of Bob's Y, that the Bob's input and Bob's output, and the vice versa. And using these two conditions, these two assumptions, this joint statistics can be written in terms of this one. It's called the factorizability condition. That is, you can see simply here that P probability of A, that's the input, the output of A is independent of the Bob's input or Bob's output, only dependent on the Alice's input, X. Here, AX means that is whenever X is chosen, Alice performs a measurement AX. Whenever X equal to, when Bob receives the input Y, Bob performs the measurement of B1. So the realism and locality, local realism actually implies a factorizability condition. There is a probability. Mathematically, that means this. But in quantum theory, the source can emit the quantum state, which is maybe entangled. So this entangled state is shared between Alice and Bob. We can also calculate the joint statistics by considering the this bond. That is, that's a rho that is shared between Alice and Bob, and we have two positive operators MAXA and MBYB, and we can calculate the joint statistics. It is well known. This is very much well known that to the community that this quantum statistics, if suitable states, rho, suitable measurements AX and BY are chosen by Alice and Bob, in such a case, this factorizability condition is not compatible with the quantum theory, and that is elegantly demonstrated to the Bell inequality. And this incompatibility is known as the non-locality. So let me quickly go through this QIQT23 inequality. That is the simplest Bell inequality we have in two input, two output scenario. That is this X and Y. Against X is 1 and 2, Y can be 1 and 2, and in quantum theory they can share a state psi. But in classical theory, you can always formulate this delta, which is the QIQT23 expression, which is A1 plus A2 B1, A1 minus A2 B2. Here, A1 and A2 corresponds to the input received by X by Alice 1, 2. So upon receiving the input 1, Alice performs measurement A1, receiving the input A2, Alice performs measurement B2, A2, and similarly for Bob. And in classically, if the factorizability condition holds, this condition holds, that means the local realism holds. It is simple to show that this delta expression QIQT23 inequality is bounded by 2. But in quantum theory, we can consider that Alice and Bob, they are sharing an entangled state and the suitable positive operators, so that we can get values. Sometimes we can get values of this QIQT23 expression delta, and we get them. And optimal quantum value is 2, and that was calculated by Seelson in 1980. But there are many textbooks and many literature you can find that to get the 2√2, you need to assume that A1, the observable of Alice, is sigma x plus sigma z by √2. The other observable sigma x minus sigma z by √2, and Bob's observable are sigma z and sigma x. And if you take a state like this one, it's a maximally entangled state, you can get these two. Now comes a very interesting point, that how do you know this is a maximum value? Because this is all derived by using the qubit system. You may be considering the higher dimensional system and you can get more than 2. But this is not true actually, because this is the power of the Bell's theorem once again. That is, the optimal value is remains 2√2. It is irrespective of the dimension you use. And irrespective of the dimension you use and whatever the measurement you want to choose. Let me show it in a different way because this is important, because in the device-independent self-testing, you have no idea about the inner working of the devices, whether it's a qubit system or 2-qubit system. That means the independent of the dimensionality is important. So device-independent self-testing requires the devices of Alice's and Bob's. They are completely black boxes. There is no way to know the inner working of the devices, and the dimension of the system remains unknown. That means it can be any arbitrary dimension. In order to prove it, we actually introduce a very elegant method. We consider a positive operator. This positive operator we can consider as eta, which is written in this manner, and half is introduced for a mathematical convenience. There's some omega-1 and omega-2, and they are the positive numbers, and L1 and L2 are the positive operators. So definitely for any state psi, any arbitrary state, eta is operator remains the positive semi-definite. Now for our purpose, we introduce the L1 and L2 in this manner. So we consider L1 equal to A1 plus A2 by omega-1 minus B1. Here, our plan is to normalize this A1 plus A2. That is, this omega-1 is actually a normalization. So that is actually the norm of A1 plus A2 psi A2 for any arbitrary state. And similarly for omega-2, we consider. Now, if you put this equation 1 to this here in eta, a little calculation is required, you will find that in quantum theory, eta q will be giving you omega-1 plus omega-2 minus delta. That is the one we want, because delta is the Bell expression in quantum theory. So by rearranging, we can write the delta q equal to omega-1 plus omega-2 minus. Now you see, as I mentioned, that eta is a positive operator, positive semi-definite. So to get the maximum value of delta, we need that eta q has to be 0. There's no other way possible. So that means the optimal value of delta can be written in this manner. That is maximum of omega-1 plus omega-2, which can be written in this way, because omega-1, as I mentioned, is the norm of the A1 plus A2 psi, and omega-2 is in this manner. So we can simply write this way. So what we find is that to get the maximum value, what is the maximum value? Maximum value can be obtained when A1, A2 are mutually anti-commutative. So what we get is that we get the two value back, and when A1 and A2 are mutually anti-commutative. And you see that I have not considered any dimension yet. So first condition we get, that is when you get the optimal value, Alice's observables has to be mutually anti-commutative. And this condition gives the value, fixes the value of omega-1 and omega-2, which is nothing but 2. Now, once again, when you get the optimal value, this eta had to be 0. So if you see the eta once again, then you'll find that eta is actually this quantity. So as I mentioned, omega-1 and omega-2 are positive quantities. Then to get the eta equal to 0, both L1 and L2 has to be 0. So what we find is that L1 equal to 0 implies that is B1 equal to B1 plus A2 by root 2, and B2 is also equal to A1 minus A2 by root 2. That gives the simple that B1, B2 has to be anti-commutative. So what we obtain up to now, that optimal quantum value is obtained to when A1, A2 is anti-commutative, B1, B2 are also anti-commutative. Now, again, we can rewrite by using this B1 equal to and B2 equal to this, we can rewrite the CHSH expression in this manner. So root 2 into this one. The expectation value of B1 can separate B1 and B2 can separate B2. Definitely, this B1 is on the Alice's subspace, and this B2 is also in the Alice's subspace, but only the form is same. So the optimal quantum value requires both of them has to be 1. That means there should be a state, for which the B1 and B2, the state is actually eigenstate of B1 tensor product B1 and B2 tensor product B2, and that fixes the state. So the shared entangled state we write, there's a little more calculation required. We write is in this form. This is actually a pure state, it can be proved, and you can simply check, and this is a maximally entangled state. If you take the partial test, then this is actually ID. So in that case, you will get identity by. Now then what we obtain from here? You see that in the whole derivation, we have not considered any dimensions. So then optimal quantum value of CHSH actually inequality fixes the following. What it fixes about the, I started with the black box devices, had no idea about the dimension of the system. But what we obtain is that from this optimal quantum value is that Alice and Bob's observables are mutually anti-common, and that is the demand. Without this, the value will not be true. And the shared state is maximally entangled state. And that is the two requirement, I mean, two properties of the whole experiment we fixed. And this is a kind of the self-testing of the quantum devices and the state in quantum theory. And through that is obtained the optimal quantum violation of a Bell inequality, the simplest Bell inequality, CHSH inequality. Of course, there are many such inequalities are there, and one can calculate the optimal quantum value, and that can be useful for the self-testing. But it's very hard to calculate the optimal quantum value analytically or any arbitrary form of inequalities. Okay, so these are the basic of this the whole why CHSH inequality is important, why it provides the device independent certification schemes, because its optimal quantum value actually fixes the quantum correlations. I mean, the PABXY, I mean, in this process, actually, the input-output statistics is uniquely fixed when we get the value, optimal quantum value. Well, now going to the next part, self-testing of unsharp instruments. Now coming to the very important question. The same Bell experiment I have here. As I mentioned, the optimal quantum value is 2√2, and there is a little mismatch. This beta should be delta because it was a picture, so I couldn't change it. So now, as I mentioned, this is obtained only when you have maximally entangled states shared between Alice and Bob, and local observables are mutually anti-common. Now, what happens in between? If we get a 2.5, for example, what you can say about the system? What you can certify? You can certify nothing actually. So the important question here is that let's the value of this the CHSH expression is in between 2 and 2. So it can come from 3 different forms. For example, the state rho AB is not maximally entangled state. It may be a pure state, but not maximally entangled state. It can be a mixed state. Or it can be, there's another source of error is possible when the measurement is not perfect. That is Alice and Bob, they're not performing the sharp measurement or projective measurement, they're performing some POVMs or positive operator value measures, the unsharp measurement. That can also reduce the value of CHSH expression. And another thing is possible that Alice and Bob were required to perform the mutually anti-commuting observables, but they're actually performing not anti-commuting, they're performing non-commuting observables. Okay. That can be another source. In this work published in 2023, and Prabhupada and I showed that actually what we can say is that the imperfection, that is the value less than 2 is coming due to only the imperfect measurements. Unsharp measurements. That is, for example, here we consider that Alice's observable is always sharp, but Bob performs the unsharp measurements, and that we can certify. So to certify that unsharp measurements, we have to certify again that the Alice and Bob performing the anti-commuting observables, and Bob's observables anti-commuting, but unsharp versions, and rho ABC maximally entangled state. But there's a problem. Problem is the Neumark's theorem. What it says? It says that any non-projective measurement, including unsharp measurements, can be interpreted as a projective measurement in suitable higher dimension. That means, if I claim here that I am actually performing unsharp measurement for the Bob, but Neumark's theorem says that actually you have no dimension restriction because device independent certification, we have no dimension restriction. So then unsharp measurement can be always interpreted as a sharp measurement in a higher dimension. But sharp measurement for what? Sharp measurement of 2 non-commuting observables. So they are not reaching the anti-commuting observables. That is why value is less. So how to then, due to the Neumark's theorem, it's very challenging. Because how to then certify that exactly that what is that the value less than 2 is coming due to the unsharp measurement. But because there are 3 more sources are there, and Neumark's theorem says there is no unsharp measurement exists because any unsharp measurement is a sharp measurement in the higher dimension. So what we do is that we show that sequential Bell test has the potential to self-test the unsharp quantum instrument by circumventing the Neumark's theorem. How it is? That intuitively, let us consider a sequential measurement scenario. There's a one Alice who always performs sharp measurement, and there's a Bob 1 and there's a Bob 2. That means they perform the measurement sequentially. And it is again the same Bell-CHSH scenario, that is receiving one input, two input by Alice. This Bob1 is also receiving two inputs, Bob2 is receiving two inputs. But the important thing is that if you accept a Neumark's theorem, that is, Bob1 is not performing unsharp measurement, but actually performing the true and non-commuting observables in a higher dimension. But the important fact is that even if it's a non-commuting observable measurement, it's a sharp measurement. Sharp measurement always disturbs the state. That means if you consider that Alice and Bob are getting a violation, then if you perform the measurement of sharp measurement of anti-commuting, non-commuting observables, this state, entangled state, will be completely destroyed. And there is no way to get the violation of Alice and Bob. So once we get the violation of Alice and Bob too, and we can certify it, certification is a little tricky here because you have to certify two well violations. So what we show is that the violation of Alice and Bob 1, quantum violation of Alice and Bob 1, or CHSH value of Alice and Bob 1 and CHSH value of Alice and Bob 2, they are definitely suboptimal because you are performing a measurement here unsharply, you cannot never get to. But these two violations, this suboptimal violation, form an optimal pair, and that enables us to certify thus the state is maximally entangled state. Alice performing mutually anti-commuting observable, Bob 1 performing mutually anti-commuting observables, and the sharpness parameter of Bob. How do we do it? And it is a very technical questions, and there are some calculations are involved. I'm not showing this. So what I want to say is that Bob 1 definitely performing a sharp measurement, unsharp measurement, that's the POVMs. Otherwise, the quantum violation of CHSH inequality will not be extended to Alice and Bob 2. So this unsharp measurement is characterized by POVM. This is the E is the POVM here, and K is the Krauss operator or some the measurement operator. And what you can see is that you can calculate the reduced density matrix for Alice and Bob 2. It can be written in this manner. I wrote it K, so K can be 2 here for Bob 2. So then we can calculate in this way the average state that is shared between Alice and Bob 2. Then you can calculate the Bell inequality and CHSH inequality value from here. Okay, this is the POVM we have considered. This is a 16 POVM or one parameter family POVM that can be written in this manner, where this pi plus and pi minus are the identity D, because I have not considered any dimension here. So the challenge is the whole challenge of this work is to derive the suboptimal values without using the dimensions. So one can write the measurement operators in this manner, because K equal to root E, and then what is the alpha K and beta K, that is the calculational details. That's not very much important here. You can follow my paper. So what we obtain is that the maximum quantum value that was CHSH expression for Alice and Bob 1 can be calculated. So delta 1 is the quantum CHSH value of this Alice and Bob 1. This is lambda 1 into delta. What is lambda here? Lambda is the unsharp parameter of the Bob 1, which is introduced here. Okay. So for y equal to 1, for k equal to 1, you have lambda 1. And that is the one we want to certify. Good. So, so Alice and Bob 1 maximum quantum values is lambda 1 into delta optimal. You can see this is already known because we already calculated delta optimal for CHSH inequalities 2. And that already fixes the mutually anti-commuting observables and maximally entangled state. So then this is the reduced state. This is not important here, important, but it is very hard to follow in this short duration. So now we want to calculate the Alice and Bob 2 CHSH value. If you calculate for delta 2, that is the Alice and Bob 2 quantum CHSH value, then we get this kind of expression. We wrote it in this manner, and where V1 tilde and V2 tilde can be written in this form. Okay, I'm not going to the details, but you can see simply that is we can use this elegant approach I already mentioned, sometimes called the sum of square approach, to obtain the maximum value of this Alice Bob 2 quantum violation of CHSH. Well, that can be done in this way. So what you obtain is that we obtain. Okay. So what you obtain is that the CHSH value of Alice and Bob 2 can be written in this manner. So here you can see simply again what we get the delta optimal here, and this this quantity is only dependent on delta optimal, which is already proved quite true. And this is dependent only on lambda 1. And now CHSH value for Alice Bob 1 is also dependent on lambda 1 if we consider this delta optimal value as set. So what we can do is that we can write delta 2, that's the Alice Bob 2 CHSH value in terms of the delta 1, Alice Bob 1 CHSH value. If you can write it, we get similar this kind of expression. This is very important and interesting one. Because you see, now it is a kind of trade-off relation, right? So if it increases, you can see that this value decreases. And if it is decreases, this value increases. So how much disturbance is caused by the Bob 1, that can be reflected to the violation of Alice and Bob 2. Okay? So if you plot it, you get this type of plot. Again, this B has to be replaced by delta, and this B has to be replaced by delta. Okay, so you can see this green region is actually classical. So there is no trade-off possible. That means in classically, Bob 1 does not disturb the state so that Bob 2's value can be changed. Okay, so this is the flat one. There's no trade-off relation is possible. But you see the blue car, this is the trade-off car. So you can see this value depending upon the Bob B1, I mean delta 1's value, the Alice to Bob 1 violation increases, then that will be Alice to Bob 2 violation decreases, and vice versa. Now, how can you certify that? Certify the unsharpness parameter. You see, in this blue line, there is this blue line, every point in the blue line is actually certify a particular lambda 1 unsharpness parameter. How? You see, as I mentioned that both of them actually dependent on lambda 1. That means experimentally, if you obtain some value of delta 2 and some value of delta 1, for example, let's experimentally you obtain delta 1 equal to delta 2 equal to 8 root 2 by 5. It is only one incidence when you can get equality. I took this particular point. So in that case, what you can say about it? So you can just simply say that is this point is coming because there's a particular lambda 1 is involved. So then every point here actually certify a particular lambda. And these regions are actually the suboptimal ranges. That is not can be useful for the certifications, and only these blue lines can be useful for certification. So every point here is a particular lambda. That means by which lambda 1, that is which unsharpness parameter Bob 1 is using, that can be certified on this one. So that means this delta 1 and delta 2, these two Bell violation, actually the suboptimal, but they jointly become an optimal pair. An optimal pair certifies the following again. So Alice measurement, the sharp measurement of two mutually anti-commuting observables. Bob's measurement, Bob 1 performs unsharp measurement corresponding to two mutually anti-commuting observables. And also, I have not shown here, but it can be shown that the set of observables for Bob 1 and Bob 2 are the same. So one may consider that why you are considering the same observable, because you cannot assume anything. Why you can taking the same observable for Bob 1 and Bob 2, same set of observables. We have not assumed it. We have proved it that they, for the optimal values, you need Bob 1 and Bob 2's observables are same. Okay. And again, to get the root 2 value, because delta optimal was there as well. So then Alice and Bob 1 share a maximal entangled steadily arbitrary dimension. Along with that, this optimal pair certifies that unsharpness parameter of lambda 1 of the Bob 1. Definitely, in a real experimental scenario, you can never get this theoretical value, whatever ideal scenarios values. But in such a case, also we can actually introduce the robust certification of unsharpness parameter, because experimentally you can never get the value you want. And in such a case, you can actually certify a range of values, not the exactly the values this blue curve I mentioned, but exactly that values cannot be certified, but the range of values can be certified. Okay, so that was extended for any other form of inequalities, and so on for two parameter can be certified together. But that I'm skipping this. The next part of my talk is the device independent certification of degeneracy-breaking method. Let me once again say that is device independent belt test require the dimension independence. That is I already mentioned. And as I mentioned, optimal belt tests locally mutually anti-commuting observables in any arbitrary dimension. Now, any arbitrary dimension, for example, I have a dimension 4, but my observables are dichotomic. That means there is a degeneracy is there. That means, two of the, maybe in a symmetric scenario, if Alice and Bob sharing a pair of entangled states, okay. In such a case, Bell violation remains same. That is, two value remains same. But Bob now has 2 qubits. 2 qubits means it's actually the 4-dimensional system. But the observable are dichotomic, so that means plus minus 1 eigenvalues. So then plus 1 has 2 eigenstates and minus 1 has 2 eigenstates. So we have a degeneracy. Okay. Can you certify that how the way the Bob or Alice perform the measurement, either it's a degeneracy preserving or a degeneracy measuring, degeneracy preserving or degeneracy breaking? Actually, it is independent, irrespective of the fact. If Bob or Alice performs a degeneracy breaking or degeneracy preserving measurements, it does not matter, because this trace row M, a particular measurement of M, whether you are performing degeneracy breaking or degeneracy preserving, it does not matter, because the statistics, first statistics remains unchanged due to the way you are performing the measurement. But we show that how a degeneracy breaking measurement can be certified through the Bell test. So let me just for a brief overview, what is degeneracy breaking measurement? Let I have an observable B which has 4 eigenstates and can be written in this manner. It is a kind of 2 qubit observables. There are 4 eigenstates. That's a 1, 2, 3, and 4. And a 1 and 2 has a positive plus eigenstate, and 3 and 4 has a minus eigenstate. So if you perform this row B, trace row B for any arbitrary state, that remains unchanged the way you perform the measurement, because this is simply this one you are calculating. That's a simple algebraic calculation. But although the statistics remains unchanged, whether the state reduction remains unchanged? Answer is no. The reduced state for the measurement of degeneracy preserving here will be different than the degeneracy breaking. How it is so? Because if you calculate the reduced state for row DP, degeneracy preserving, then you can calculate the state reduction in this way, because this is your projector, because you are not distinguished you are doing the Luder measurements. So then 1 1 plus 2 to row into 1 1 2 2, and similarly for here. But here for the degeneracy breaking measurement, fully degeneracy breaking measurement, you perform the measurement in this way. In such a case, your state reduction will be in this way. But you see, there is a term, there's a correlation term is possible. It's a cross term, because 1 and 2 cross term and 2 and 1 cross term is possible. Similarly, here 3 and 4 cross term and 4 and 3 cross term is possible. But here there is no cross term. So these two states are not equal. But how can I test it? We go for the Bell test. That is, we show that device independently, without knowing the inner working of the device, without knowing the dimension of the system, we can certify whether Bob 1 is performing a degeneracy breaking measurement or degeneracy preserving measurement. And that is also again done with the sequential scenario. Because in the sequential scenario, if Bob 1 performs a degeneracy breaking measurement, the state will be disturbed more than the degeneracy preserving measurement. So there are many degrees of degeneracy breaking measurement possible. So the state will be disturbed accordingly, and that can be captured by Alice and Bob. So a simple idea. But how to perform degeneracy breaking measurement? To perform a degeneracy breaking measurement, you have to perform a commuting observable before your original observable. For example, your original observable you want to perform is B. That is, this is the P plus and P minus. These are the 2 eigenstates having eigenvalue +1. These are the 2 eigenstates having eigenvalue -1. So, but to breaking the degeneracy, that means you want to perform that individual projectors, you need to perform a commuting observable just before it. Because it's a commuting observable, it will not disturb the system, but actually this type of projective measurement you can employ. Instead of this P plus and P minus measurement, you can employ the measurement in this way. I mean, this way you can perform the measurement. And initially, degeneracy preserving measurement you are performing this way, but a degeneracy breaking measurement you are performing this way. So 2 different state reduction will occur. And I mean, for the entangled scenario, you can say that is in this case, degeneracy breaking measurement, your system of entanglement will be disturbed more than degeneracy preserving measurement. But the challenge is how to certify. So we took this particular scenario because we have no dimension issues. So this was By and By1, P1 to maybe UI is the original observables, and these are the observables that is required, the commuting observable that is required to break the degeneracy. Okay. So now we introduce a term called GPOVM measurement. So how many POVM you want to perform? Because if Bob1 performs half measurement, there is no way you can get any entanglement demands between Alice and Bob2, and no violation you can get. So even if it's a degeneracy breaking measurement, so I should call this a degeneracy breaking POVMs. Okay, because this has to be the POVMs answer measurement. Otherwise, no entanglement will reduce. It's either degeneracy breaking or degeneracy preserving. It doesn't matter. So we introduced the term GPOVM measurement. When G equal to 2, that's the usual one, degeneracy preserving measurement. That's already considered in the last half an hour of this talk. But G greater than 2, we get partially degeneracy breaking measurement. That is degree of degeneracy you are breaking. And G equal to D, which is the fully degeneracy breaking. Okay. So can we distinguish between all three without knowing the inner working of the device, without knowing the dimension? So as I already mentioned, Alice to Bob1 quantum CHSH value, which is nothing but delta 1, lambda 1 delta optima. That's already considered. Where lambda 1 is the unsharpness of this Bob1. As I already mentioned, that Alice to Bob1 value is irrespective of the fact that whether you are performing degeneracy breaking or degeneracy preserving. The change comes in the state reduction. So the change comes in the Alice and Bob2 quantum violation of the CHSH. So then for any arbitrary G, you can write delta 1, that's the CHSH value for Alice and Bob1 remains same. So this is the construction of the reduced states and the POVMs. So for G equal to 4, we can write such kind of POVMs in an arbitrary dimension. G equal to 3, we can write this way. And G equal to 3 is already known to us. And the challenge will be to calculate the measurement operator from these POVMs. And that we actually did. Okay. So now for G equal to 2, this result is already known. I discussed already in the last part of the talk. And the second one I discussed is the only one, that's G equal to 4. That is, we are considering G equal to 4. That means we are considering 4 POVMs by Bob1 with the unsharpness parameter lambda 1. So we constructed the Cauchy operator for that, and that's the alpha 4 and beta 4 at the coefficient that is required, because alpha 4 and beta 4 are here. And what we calculate that Alice to Bob2, when G equal to 4, when you are considering 4 POVM by Bob1, in such a case, you get this one. That's an interesting result, because it remains again, delta optimal comes back. And this alpha 4 and beta 4, you can see they are only dependent on lambda 1. So if you write in terms of lambda 1, you can write this way. Okay. Similarly, what you can do is that for G equal to 3, let's consider 3 POVM. Actually, you consider up to 5 POVM, because after 5 POVMs, you cannot get any because any quantum violation for values to Bob. Coming to that. And when G equal to 3, you can also write the Alice and Bob2 CHSH value in terms of this. You can see that it's also dependent on lambda 1 and on the delta optima. No dimensions are used. It's completely independent of dimension. All the analytical data. Okay, now, if we plot them, that is again Alice to Bob1 quantum violation and Alice to Bob2 quantum violation. Again, you have to B has to be displaced by delta here, because it's the copy-paste image. Okay, you can see for G equal to 2, I got a blue curve that is already known, because the degeneracy preserving, earlier we have considered without considering any degeneracy preserving or degeneracy breaking one. That's a known result to us now. For G equal to 3, this is the black. You see, there is no overlap. G equal to 4, there is a red one. And G equal to 5, this is this one. I have not plotted after G equal to 5, because after G equal to 5 and G equal to 6, if you consider what happens if the state is so much disturbed, you cannot get any quantum violation of Alice and Bob. So we have not gone to that. So you see that how the certification occurs. How can you certify that whether I am performing a degeneracy breaking measurement or degeneracy breaking measurement, degeneracy preserving measurement? Because this is the statistics we get in experimental scenario. For example, you can consider, I have a perfect instrument and I can measure this. So I calculate the Alice and Bob1 measurements and Alice and Bob2 measurements. How can you certify? Look, for example, it's a red dot here. If the red dot comes, definitely we have a 2 values, that is Alice and Bob1 values and Alice and Bob2 values, CHSH values. So this value can only be obtained when G equal to 2. If it is G equal to 3, is value, because this is a non-overlapping and this black curve is lower than this G equal to 2, you can always get the lower values of it. So these values will never match. Similarly, for this this green one, if you get the CHSH value for Alice and Bob 1, Alice and Bob 2, such that this green dot is realized, in such a case, you are definitely sure that it is not G equal to 3, 4, or 5. In the G equal to 4 and 5, these are in the, but it can be G equal to so. So you can get actually an upper bound. Actually, you can say it can be 2, can be 3, but it cannot be 4 and 5. So this is the way we certify that how many POVMs Bob uses to perform the measurement can be certified in this manner. So I think I'm already exhausted my time. So let me summarize these things. So I introduced the notion of device independent scenario, self-testing in the CHSH scenario. And I discussed actually the elegant sum of square approach to derive the optimal quantum violation of CHSH inequality in device independent way. I would suggest all of you to see this derivation in this paper. Further, I demonstrated the self-testing of unstuck quantum instrument and using the sequential Bell test as a tool. And finally, I demonstrated the self-testing of degeneracy-breaking measurement using sequential Bell test. And thank you very much.
Thank you, Alok, for your presentation. So now we have enough time for the introduction. So is there any questions? Then audience may ask. Alok, can you little bit explain this degeneracy breaking measurement little bit?
Yeah. Yeah. So what happens to that is that if you calculate this row B, that means it is a given state, B is given, whatever measurement, whatever the way you perform the measurement, whatever the way you collect the statistic, it does not matter. You can do one thing. You can do perform measurement 1 1 first. So trace row 1 1, and then trace row 2 2, and then calculate 3 3 and 4 4, and then collect the statistics, and then just arrange it algebraically. Probability of getting 1, probability of getting 2, and then minus probability of getting 3 minus.
So Alok, here row is a single qubit or?
It doesn't matter. It doesn't matter because I just said, yeah. I mean, here row is a simple state. I mean, I'm not going to the entangled state now.
Single qubit state, right?
I have not. Here
because,
you cannot say a single qubit because it's a 4 dimension. So it's a 4-dimensional state.
4 dimension is it correct? But here you are taking this K1 bra1 plus K2 bra2.
Yeah, it's a 4 eigenstate of the observable.
It defines a single means single QIQT, I think, means 4
no, it's
dimension.
not the case because you can see that 1 is a 0 0 and 1 is a 0 0, 2 is a 0 1 1, then 3 is a 1 0 and 4.
Okay. The notation is like this. Okay.
Yeah, I have not mentioned anything. It's completely general. So in such a case, if you perform the measurement, it does not give you the way you perform the measurement. But if you see the reduced state remains different because if you separately perform 1 1 first and then 2 2 first, that will be this degeneracy breaking scheme. And if you perform this one, I perform 1 1 and 2 2 together, and there's a projector is P plus here, and then this is the state error. But that cannot be captured by this one. This row we cannot capture it.
So degeneracy means here can we relate it to the this eigenvalue?
Yes, this is eigenvalue because it is 1 1 and 2 2 has the eigenvalue plus, and 3 3 and 4 4 has the eigenvalue minus.
Okay.
The similar thing will be happen to the entanglement. If you consider an entangled state, what happens is that your if you consider the unsharp POVMs, so then depending upon the number of POVM you are considering, the state will be disturbed accordingly.
Okay, fine.
Hello, sir. Can I have a question?
Yes.
Sir, in CHS, case, for the optimal case, the resources are like share entangled state and the other one. But for your scenario, the optimal resources will be same. Or
yeah, I can start from the beginning. Yeah. So this psi here is normally considered as a maximally entangled state in two-qubit system. But there are dimension is in quantum theory is a resource. But there are many protocols. For example, the BB84 is the famous protocol. That protocol is compromised if you consider the dimension of the system. So dimension of the system is known to everyone. Then many protocol can be compromised. So you have to go to the dimension independence now. What I tried to do in this whole talk is that I tried to not to consider any dimension of the system, because I know there is a dimension definitely is there, but it's an unknown one. I mean, that can be any higher dimension is possible, whatever you can think of. Okay, so this psi is a maximally entangled state here, but I consider that psi, I derive the psi can be like this one. I mean, in the row, I mean, in terms of psi, it will be very difficult to write, but in the row AB is a pure state, definitely you can prove, because these all BIs are, I forgot to mention, this all BI tensor product BI are actually commuting observables. And there are d square minus 1 number of commuting observables. I mean, that answers your question, or no, I think I dragged something.
it's important.
Partly, okay. So you can reframe once again. Go on. No? Okay.
So if there is no question, then I would like to thank Dr. Alok for his good presentation.
Thank you, Sutra.
Thank you, Alok.
Made you so much.